Hello my friends and welcome back to the You Can Do TV channel.
Stone handling underground follows its own logic inside Hallensassen, where a Lungby L15 handles the final macadam reception. Material arrives continuously, fed into confined tunnel space without room for hesitation. The loader positions, scoops, and transfers aggregate to maintain steady flow. Space control matters more than speed here. Each pass balances bucket load with tunnel clearance, keeping traffic paths usable. That narrow margin keeps focus sharp. Macadam grading and placement support drainage and structural layers deeper in the project. This sequence marks the last operation performed in these tunnels. Closing work matters. Operator's Guide: the MATISA C75 to 2C through ballast cleaning and renewal while the rail network stays in service. Marty Deutschland applies a tunnel expansion system that allows excavation, support, and renewal to proceed without stopping trains. Temporary inner structures guide loads, while the existing tunnel shell remains active. This approach keeps rail service uninterrupted, while structural capacity is gradually increased. Keeping trains moving, while work continues underneath, already sets the tone for how tight this operation feels. Surveying and reinforcement take place first, mapping clearances and stabilizing the old lining before enlargement advances. Geometric checks ensure the original tunnel profile can safely accept additional loads during expansion. Support frames are installed inside the tunnel to carry rail traffic loads. This inner structure becomes the working envelope, separating live operation from construction zones. That separation is doing more work than it looks. Load paths are clearly redirected through the temporary supports at this stage. Once secured, controlled excavation removes material behind the supports in defined sections. Expansion progresses step by step, with excavation depth adjusted to maintain structural balance. Spoil is removed continuously to keep access paths clear. Material removal rates are coordinated with support installation to avoid overstressing the surrounding ground. New concrete lining follows closely, locking geometry into place before the next section opens. There's no room for guesswork when trains are still passing above. Section-by-section verification prevents cumulative alignment drift along the tunnel length. Each segment is verified for alignment and clearance before moving forward. Electrical systems remain active throughout, requiring constant coordination between civil work and rail operations. Overhead line protection and clearance checks run alongside structural tasks. One wrong sequence here would stop everything, so the order matters more than speed. Work windows are tightly defined to match rail operating constraints. Equipment movement stays compact to fit within the inner tunnel limits. As widening reaches full profile, permanent tunnel structures replace temporary supports. Finishing work integrates drainage, cable routes, and final surfaces without altering rail alignment. Seeing old and new structures coexist this closely feels unreal in the best way. Final geometry confirms compatibility with long-term railway operation requirements. Final checks confirm stability under live loads, completing the tunnel expansion while trains never left service. Traffic keeps moving while crews trench, install, and weld new water pipes along St. George's Road in Preston for the M40 project. The center median is opened, pipes are aligned, and joints are welded before controlled backfilling restores the roadway. Welding quality here directly affects long-term water reliability beneath daily traffic loads. Seeing pipes disappear under an active road hits differently today. High-output ballast renewal takes a different form when the MATISA C75 2C operates along active rail lines as a fully integrated moving system. Built by MATISA for demanding railway networks, this machine combines excavation, screening, and ballast return into one continuous workflow. The result is renewal work that stays contained within the track window rather than spreading across multiple machines. Ballast enters the system beneath the rails, where cutting chains lift worn material and guide it into internal conveyors. Screening units separate reusable stone from fines, maintaining track support quality while reducing waste. This separation step directly controls how long the renewed track will hold geometry under traffic. Reusable ballast is cleaned and routed back toward the track, while excess material is directed away without interrupting motion. Material flow remains constant as the C75 2C advances, with ramp-in and ramp-out sections allowing smooth engagement and disengagement on live networks. That flexibility keeps setup time short and production time focused. You don't expect something this complex to move forward so steadily, yet it does. Conveyors, screens, and return paths stay synchronized to avoid buildup or imbalance. New ballast is introduced and distributed precisely along the sleeper bed, restoring support depth and alignment. Tamping and leveling operations follow closely, locking the renewed structure into place. This is where renewal stops being theory and becomes load-bearing reality. The machine's length allows multiple tasks to overlap, compressing what would normally require separate passes. Operator control centers manage flow rates, cutting depth, and distribution to match local track conditions. Adjustments are made in real time as ballast composition changes. Small changes here decide whether the track settles evenly or keeps shifting afterward. Despite the scale, the system relies on disciplined sequencing rather than brute force. As the MATISA C75 2C clears a section, finished track emerges behind it, ready for service without extended downtime. Railways gain cleaned ballast, restored geometry, and consistent support in a single pass. Seeing a full renewal completed without breaking the rhythm of the line feels surprisingly calm. That balance between output and control defines how modern ballast cleaning keeps networks moving. Controlled force defines how the KAM-PSAXCICEC 250 handles an 820-ton Type 1 box girder for full-span bridge launching in Taichung. Hydraulic systems align the girder precisely on temporary supports before synchronized pushing units take over. Load distribution remains balanced as the span advances millimeter by millimeter along the guide path. That moment where everything stays perfectly steady feels tense in a good way. The Taiwan High-Speed Rail Project C250 relies on this method to place spans safely without cranes. No room for hesitation here. Speed changes expectations with LPC precast concrete house construction designed for 1 to 3 story homes and villas. Factory-made panels arrive ready for assembly, allowing a full structure to rise with minimal labor and no on-site concrete work. That pace instantly resets how long a house is supposed to take. Day 1 focuses on logistics and structure. Equipment and prefabricated materials enter the site, followed by panel assembly and ring beam installation. Lightweight steel roof trusses are positioned to lock the main frame together. Seeing a solid shell stand this early feels unreal in the best way. Day 2 shifts to fast wall installation, completing exterior and interior panels while continuing roof truss alignment. The system relies on dry connections, eliminating mortar, scaffolding, and temporary formwork. Everything clicks into place without the usual mess. Day 3 applies sprayed insulation across the envelope, sealing thermal performance quickly and evenly. This layer supports energy efficiency and long-term comfort. That smooth coverage hints at how controlled the whole system is. Day 4 introduces prefabricated interior finishes. Walls, ceilings, and built-in components are installed without cutting or wet trades. No piles of waste means less time cleaning and more time building. Day 5 and 6 finalize remaining assembly and detail work. Labor statistics highlight the efficiency. Main structure uses 3 workers over 2 days. Exterior finishes need 4 workers over 3 days, and interior finishes require 4 workers across 5 days. Total labor reaches only 38 workdays. That number alone says plenty. LPC houses avoid on-site concrete, reduce waste to near zero, and allow 4 to 5 skilled workers to erect an 80 square meter home in a single day. With seismic resistance above grade 8 and a lifespan reaching 80 to 100 years, this approach quietly changes how residential construction is planned. Tight urban space and a 140-year-old structure set the tone for the Scarborough Bridge underbridge reconstruction led by Network Rail. Aging timber decking and an expired structural life demanded decisive action inside a historic city. That combination already tells you this won't be routine work. Stage 1 centers on bridge deck delivery. New decks arrive under strict access limits, coordinated as a high-profile operation surrounded by daily city traffic. Every move here feels planned twice before it happens. Stage 2 builds the lifting backbone. A 500-ton crawler crane is assembled for multiple deliveries over 8 days, carrying up to 400 tons of counterweights. Residential buildings sit close by, leaving no margin for casual adjustments. This setup alone looks like a project inside the project. Stage 3 clears the way. During a 9-day railway blockade from February 13th to 23rd, crews removed the existing track and bridge decks. Lifts reach 50 tons at a 61-meter radius, relying on controlled crane work to dismantle material that has stood for generations. Hard to ignore the tension at that reach and load. Stage 4 prepares and installs the replacement structure. Weathering steel is selected to cut long-term maintenance demands. 4 new decks are positioned, each lifted at 61 tons and the same 61-meter radius. That consistency keeps risk predictable, and predictability matters here. Stage 5 restores the railway. Track installation includes a tandem lift to place the switch panel, aligning geometry before final connections lock the system together. This is where everything has to agree. Stage 6 closes the operation. Reconstruction finishes safely, within budget, and ahead of schedule. The result reflects teamwork built on accountability, collaboration, and focus. You don't beat the timeline on work like this by accident. Two parallel tunnels stretching deep beneath Doha redefine how underground transit takes shape on the Red Line North project in Qatar. WeBuild drives excavation, removes 530,000 cubic meters of material, and advances through 11.6 kilometers with strict control. That volume alone changes how scale feels underground. Sustainability targets guide every phase, proving large infrastructure can still respect environmental limits. A major refinery unit is brought back online through tightly sequenced mechanical work during the SR Cat Cracker Turnaround Event 2013. Teams move across the cracker unit with a clear order of tasks, each step tied to restoring safe and stable operation within a fixed shutdown window. Preparation focuses on isolating systems, venting lines, and opening critical sections for access. Large components are staged nearby to minimize idle time once removal begins. You can feel how every hour matters here, because delays cascade fast at this scale. Heat exchangers, piping sections, and valves are disconnected and lifted out using coordinated rigging plans. Inspection follows immediately, with internal surfaces checked for wear, fouling, and distortion. Measurements guide decisions on repair or replacement, without relying on guesswork. Reassembly then moves in reverse order, with alignment and torque values verified repeatedly across joints. Miss one setting and it shows later, so attention stays locked in the whole time. Tight clearances inside the cracker leave no room for rushed handling. Pressure testing and system checks come next, confirming integrity before any restart steps move forward. Utilities are reconnected, controls are validated, and operating conditions are stabilized in stages. Seeing multiple teams sync their timing like this explains why turnarounds are planned months ahead. The final restart restores flow through the catalytic cracker, marking the end of an intense maintenance cycle. ESSAR's Cat Cracker returns to service through coordination, judgment, and disciplined repetition under time pressure. Kiln-fired clinker bricks don't earn their durability by chance, and production at Robin reveals how controlled steps turn raw clay into building material that survives decades. The process follows the material from extraction through firing, shaping each stage around heat, pressure, and timing rather than speed. Clay is first excavated and transported to the plant, where it is crushed and blended to reach a workable consistency. Moisture levels are adjusted so the material can be shaped without cracking. This balance decides whether bricks stay stable or fail under thermal stress. The prepared clay then moves to extrusion, where continuous columns are formed and cut into individual green bricks. Cutting accuracy matters here, because later firing amplifies every dimension. Mess this step up, and the kiln won't forgive it. Freshly shaped bricks enter the drying phase. Controlled air circulation removes excess moisture while preserving internal structure. Drying too fast would cause deformation, while slow drying ties up production capacity. Dryers quietly set the rhythm for everything downstream. Once dried, bricks advance to the kiln, the core of clinker production. Inside the kiln, temperatures rise high enough to partially vitrify the clay. This firing phase densifies the bricks, closing pores and increasing strength. Color and surface texture develop here, driven by mineral content and heat exposure. This is the point where bricks stop behaving like clay and start acting like stone. Cooling follows in stages, preventing thermal shock while locking in mechanical properties. After firing, finished clinker bricks are sorted and inspected. Dimensions, color consistency, and surface quality are checked before packaging. Quality control here protects entire facades, not just single bricks. Rejected units are removed to keep batches uniform. The final bricks leave the Robin facility ready for construction use. From raw earth to hardened clinker, the sequence emphasizes control over shortcuts. Seeing students map this process makes the industry feel closer, not distant. No spectacle, just material science doing its job, one brick at a time. Surface strength and alignment decide whether a paver block performs on the ground or fails under traffic, and production at RK Tile Machinery is built around controlling those two outcomes. The video follows how red paver blocks and interlocking tiles are formed using a dedicated paver block making machine, focusing on material behavior rather than marketing claims. Raw materials are prepared in measured proportions. Crushed stone dust provides the body, OPC cement binds the mix, water activates hydration, and chemical admixtures support strength and surface finish. These ingredients are fed into mixers, where consistency matters more than speed. A dry mix won't compact evenly, and a wet one loses edge definition fast. Uniform blending ensures every mold cavity receives the same working material. Once mixed, the concrete moves to the paver block machine. The material is distributed into molds shaped for interlocking tiles and paver blocks. Vibration and compaction follow, forcing air out and locking particles together. That vibration does more work than the steel frame around it. Compaction pressure determines density, which later controls load resistance and wear. Color application and surface treatment come next for red paver blocks. Pigments and surface layers are applied to achieve uniform tone and finish. The process avoids pooling or streaking by controlling layer thickness. This is where visual appeal meets mechanical discipline. A glossy surface still has to survive foot traffic, parking loads, and weather cycles. After forming, fresh blocks are released from the molds and moved for curing. Curing allows cement hydration to progress, building internal strength over time. Conditions are managed, so blocks gain durability without surface cracking. Skip proper curing, and the blocks might look ready long before they actually are. This stage quietly separates decorative concrete from structural paving. As curing progresses, blocks are handled and stacked for further inspection. Interlocking geometry is checked to ensure consistent fit during installation. Surface finish, color consistency, and edge integrity are reviewed. One uneven edge can disrupt an entire pavement pattern. Blocks that fail visual or dimensional checks are removed to keep batches uniform. Supporting equipment plays a steady role throughout the process. Pan mixers, color mixers, vibration tables, and molds made from plastic, rubber, silicone, or PVC work together to maintain repeatability. These tools allow different tile patterns and finishes to move through the same production flow without disruption. Flexibility here saves time without cutting corners. By the end, finished red paver blocks and interlocking tiles are ready for dispatch. From raw stone dust to finished paving units, the sequence emphasizes control at each step, rather than rushing output. Seeing blocks come off the line like this explains why pavements fail early or last for years. No shortcuts, no theatrics, just concrete shaped to handle real-world use.
Every SVEL power transformer is engineered to deliver stable voltage under demanding conditions. Electrical steel sheets are prepared to form the magnetic core. Each lamination is stacked to minimize energy loss and keep idle power waste 35% lower. This efficiency level is a major step forward for industrial energy systems. The core's low noise ensures smooth performance under heavy load. Windings are made from transposed conductors that enhance strength and resist short-circuit stress. The geometry of each winding is calibrated to perfection. Reduced additional losses extend the transformer's lifespan and lower maintenance costs. That's why utilities trust SVEL units in critical grids. Before shipping, every transformer undergoes strict electrical and mechanical tests under standards like GOST, ISO, IEC, and ANSI-N. Even the smallest connection is checked twice. Operators rely on detailed readouts instead of guesswork. No component leaves the floor unverified. Decades of reliable service begin right here.
Handling steel sections up to 219 millimeters, this line produces precise profiles efficiently. At this line, steel enters as flat sheets before becoming strong, uniform tubes. The machinery works continuously, ensuring each section meets the exact dimensions needed. Operators supervise the cutting, bending, and forming stages, adjusting settings to maintain consistency. The efficiency of this line is wild. N. After welding, the tubes undergo mechanical shaping to correct minor deformations and ensure straightness. Operators check seam alignment before tubes proceed to the finishing stage. The next stage involves surface finishing, smoothing edges, and removing any rough spots from welding. Tubes are then prepared for packaging and shipment, ready to reach customers. NNN. Quality control at each stage prevents deviations, ensuring the tubes not only meet standards but also perform reliably in their intended uses. The teamwork between operators and machines is something to admire. Each movement keeps production seamless. Maintenance crews regularly calibrate machines to avoid inconsistencies. This production line is optimized for high efficiency, combining speed with precision, handling large sections up to 219 millimeters while maintaining tight tolerances. It can switch profiles quickly, minimizing downtime between production runs. Safety and ergonomics are integral, with operators positioned to intervene without risk. The result is a continuous flow of uniform tubes, demonstrating industrial expertise at every step. This production line is optimized for high efficiency, combining speed with precision, handling large sections up to 219 millimeters while maintaining tight tolerances. It can switch profiles quickly, minimizing downtime between production runs. Safety and ergonomics are integral, with operators positioned to intervene without risk. The result is a continuous flow of uniform tubes, demonstrating industrial expertise at every step.
Steel trusses spanning up to 300 feet wide are produced at Brightspan's facility in Canada, each one engineered for strength and verified step by step. The video shows how steel tubes, plates, and fittings become full structural systems, each one verified, assembled, and finished under tight inspection. Every blueprint guides the production team like a roadmap, leaving little room for error. Steel tubes first enter the CNC-controlled bending machine, where operators program exact measurements using the VemPro system. The tubes, up to 170 inches long, are shaped and then clipped at both ends for welding. Production orders include every part number and blueprint, ensuring that material selection and dimensions stay consistent. Each operator double-checks measurements before the next step begins. The organization here is no joke. Everything moves like clockwork. Next, tubes move to the cold saw and drill press, which handle diameters up to 4.5 inches and lengths reaching 48 feet. Templates guide the drill press to guarantee that holes align across repeated parts. The precision in drilling ensures all trusses fit perfectly in the field. Welders then assemble subcomponents in large welding cells, some supported by 3-ton and 5-ton cranes for the biggest trusses. The teamwork between machines and welders really stands out in this phase. The Davi roller shapes pipes to precise radii, verified against gauges before further assembly. Materials from approved suppliers undergo receiving inspection, confirming all dimensions match the drawings. Minor adjustments are made if measurements are slightly off, ensuring quality compliance. Once everything checks out, technicians weld, clean, and prepare assemblies for the next stage. The robotic welding cells handle repetitive jobs, tacking and completing welds while operators inspect for any variance. Trusses are cleaned, bundled, and labeled with part numbers for traceability. Each robot is programmed to follow a specific weld path, reducing human error. You'd almost think each weld has its own identity card here. Quality checks never stop. Each subcomponent is verified against engineering drawings, and all welders follow standardized weld procedures. The Whitney plasma punch processes 5 by 10 foot steel sheets up to half an inch thick, cutting and punching with numerical precision. Operators confirm that the right dies are installed before starting each program. Purlin production uses hydraulic presses and ironworkers to flatten, punch, and form supports for trusses. Each purlin is made from either pre-galvanized or hot-dip steel, depending on its structural role. Small parts go through a parts cleaner to remove burrs and debris before final assembly. Cleaning ensures no debris will interfere with the final weld or assembly. Finally, fully welded trusses are sent for hot dip galvanizing, a defining stage ensuring corrosion resistance. After cleaning and zinc dipping, every piece is rechecked, smoothed, bundled, and certified before shipment. Finished trusses are staged carefully to prevent damage during transport. Seeing every truss tagged and approved gives the sense that nothing leaves unfinished. Alcoa's bauxite mines in Australia, Brazil, Guinea, and Saudi Arabia extract high-quality ore. Advanced rigs and real-time tracking ensure efficiency, safety, and sustainable land restoration. The aluminium plant hums as recycled metals are collected for the first batch. The process opens with scrap sorted into buckets, each carefully weighed and recorded by the batch intelligence system. The scale of automation is impressive, with robotics handling transport seamlessly. Buckets are stored or tipped into charging baskets, then placed in the melting furnace to form a new batch. BIS calculates optimal combinations, considering over 100 properties per bucket, maximizing scrap use while reducing primary aluminium. This efficiency demonstrates how technology and sustainability work hand in hand. Once melted, molten aluminium flows to casting stations, producing ingots ready for downstream processing. Safety is enhanced throughout, with light barriers and automated cranes protecting employees. Watching these coordinated operations highlights both industrial scale and human oversight. Alumnorf's BIS transforms recycling into precise, controlled production, significantly lowering CO2 footprint. The sight of a blade gliding through solid aluminum at that speed feels unreal. Yet the Surma's 013110 does it effortlessly. The blade moves through a 12-inch billet in just 11 seconds, cutting with an in-feed speed of 1.8 inches per second. The entire motion is smooth yet forceful, showing how industrial power can stay controlled. You almost expect sparks, but it's the clean cut that steals attention. Each billet enters automatically through a full line. Manipulators position it, marking and measuring systems verify data, and stacking units take over once the cut is done. The system keeps chips to a minimum thanks to a reduced kerf width, meaning less waste and lower cost. Surface roughness stays between raw 5 and 10 micrometers, delivering clean results straight from the saw. Hard to imagine that level of finish coming directly off such a fast blade. Automation handles most of the process, while operators supervise from control panels. That mix of human oversight and mechanical precision defines efficiency here. Surma's, drawing on 5 decades of sawing innovation, continues refining its billet saws for aluminum and non-ferrous materials. You'd think the machine would roar, but instead it hums like confidence itself. It takes intense pressure to make a grinding media ball that survives thousands of crushing impacts. Glassern Machine Tools CNC lathe carves 6061 T6 aluminum into a chess rook, highlighting how technology sculpts detail from solid metal. The bright aluminum cylinder sits firmly in the three-jaw chuck of the Mori Seiki NL25OOSY 700 CNC turning center. Guided by live tooling and coordinated Y-axis and C-axis movements, the machine begins its work with steady precision. N. The cutter brushes along the 2.5-inch 6061 T6 bars, removing excess material to reveal the rook's rough outline. Every swirl of the tool marks the gradual unveiling of geometry hidden in the metal. It's surprising how a simple bar starts to hint at a chess piece, yet each pass tightens the form. The initial rough cuts are refined, focusing on the cylindrical tower and flat top that will define the rook. Watching the grooves deepen with each pass, you notice the balance between machine power and material resistance. The operator monitors spindle speed and feed rates, alternating between dry cutting at 450 SFM and wet cutting at 850 SFM, ensuring smooth surfaces and consistent material removal. N. The interplay of the Y-axis and C-axis brings contours into sharper relief. Some cuts demand live tooling to carve grooves and slots, features essential to the final shape. The precision of this setup reduces the need for manual finishing later. Once the main outline is formed, the rook rotates under the lathe as finishing passes polish the surface. Small imperfections are addressed, subtle bevels and corners are sharpened, and the silhouette becomes unmistakable. Even the smallest burrs are caught and removed, leaving a perfect edge. The final step is a detailed cleanup, removing burrs and refining edges so that the piece is complete and ready for chessboard duty. It's remarkable how a solid aluminum cylinder transforms into a detailed, elegant rook without ever leaving the machine's controlled environment. You might even chuckle imagining a chess tournament with freshly minted rook pieces still gleaming from the CNC line. Seeing the rook emerge like magic from raw aluminum is satisfying. Feels like the machine has its own artistic instinct. Dented. With up to 52 kilowatts of drive power and 6,750 Newton-meters of torque, the CTX Delta 6000 TC is made for the toughest machining demands. This machine serves industries from aerospace to transportation, where both strength and exactness matter in every detail. Its scale and performance already feel like something from the future. Each operation begins with the main and counter spindles, both capable of handling up to 52 kilowatts of drive power and delivering a massive 6,750 Newton-meters of torque. They rotate components with stability that ensures accuracy across large diameters up to 510 millimeters. You could almost call this machine a sculptor for steel. That N. The spindle speed reaches 1,000 revolutions per minute, while the milling spindle, equipped with HSK 100A or Capto C8 tooling, runs at 12,000 revolutions per minute for high-speed cutting. Automatic tool changes are handled through a chain magazine that holds 50 tools, expandable to 180, each up to 600 millimeters long and 30 kilograms in weight N. A tailstock with 150 mm quill stroke and up to 3 steady rests provide firm support for long workpieces, maintaining rigidity through complex turning and milling tasks. Every detail of the CTX Delta 6000 TC emphasizes control, balance, and reliability. Quality is critical in producing turbine shafts, transmission parts, and other high-value components. You can almost imagine this machine building jet engines all day without breaking stride. Its engineering proves why DMG Morai remains one of the leaders in hybrid machining systems worldwide.
Tons of steel and dozens of parts come together daily to form Mercedes-Benz bus chassis in Colombia. Staff and suballiers coordinate, positioning each component with exacting care. The assembly of the chassis incorporates steering boxes, motors, gearboxes, front and rear axles, and additional parts. Quality checkpoints along the line ensure every weld and connection meets strict standards. Before joining the main assembly chain, engines pass through dedicated stations. Chassis are then started for the first mechanical, electrical, and electronic evaluation. Brake testing confirms flawless operation, while emissions testing guarantees compliance with Colombian regulations. Flexibility is central. Vans, articulated buses, and high-capacity vehicles share the same production line. It's remarkable how different vehicle types are seamlessly integrated on a single assembly line. Training and pilot chains coach employees to face new production challenges, emphasizing teamwork and precision. The combination of advanced machinery, high-quality components, and skilled staff maintains the plant's global reputation. Hard to imagine the patience and coordination required to manage dozens of moving parts simultaneously. NN. Vehicles that roll off this line reflect Daimler Columbia's commitment to performance, safety, comfort, and sustainability. Seeing how each chassis progresses from frame to fully operational bus is unexpectedly satisfying. This thorough assembly ensures buses exceed customer expectations and maintain Mercedes-Benz and Thomas-built buses' worldwide leadership in the market. In bloopers of sorts. Even a slight misalignment could be hilarious if it were allowed, but everything stays tight here.
The KPS-20 CNC pinion skiving machine, crafted by Kashi Fuji and Involute Gear and Machine, revolutionizes internal gear manufacturing. Its versatility encompasses internal gear hobbing, external gear hobbing, and post-heat treatment finish hobbing, all achieved with precision and efficiency. Unlike traditional methods, KPS-20 employs a higher dimensional approach, surpassing hard rolling cutting techniques. With its innovative 6-axis CNC system, KPS-20 offers a level of control and accuracy previously unattainable. Its design incorporates a steeper slope on the base bed, facilitating swift evacuation of dry cutting chips, thus enhancing productivity and minimizing downtime. This advanced machine heralds a new era in gear manufacturing, where intricacy meets speed and precision merges with automation. The Gurutspay GSM series represents a cutting-edge advancement in integral machining solutions for rotational parts. By incorporating state-of-the-art technologies, they aims to meet the highest demands of the market, offering complete turning milling boring capabilities, up to 5 axes, with their multitask turn mills. The GSM series can efficiently machine parts up to 1.6 meters, 10 meters long, and weighing up to 20 tons, making it suitable for a wide range of industrial applications. The machines feature automatic clamping of workpieces, tool and head changes, and measurements, minimizing operator intervention and reducing time wastage. The design ensures easy access to the entire work area, facilitating loading, unloading, and intermediate operations such as measurements and tool checks. The company leverages over 50 years of experience in designing and manufacturing robust cast iron bedways and machining columns, ensuring stability and precision during operation. Programming, operation, and maintenance are streamlined for ease of use. Siemens control modules and Gurutspay specific cycles enhance interaction with the machine, while compatibility with CAM systems like Siemens NX optimizes workflow. The GSM series machines are particularly suited for industries like the press and machinery sectors, where precision, speed, and cost-effectiveness are critical for competitiveness in the European market. The GSM-16, with its unique ability to maintain exceptional turning capacity while incorporating milling capabilities, presented a solution that stood out in the market. This innovative feature not only allowed operator to tackle turning and milling operations on the same machine but also significantly reduced handling and setup times, marking a significant advancement in machining capabilities. One of the key features of the GSM-16 was its comprehensive functionality, which includes a loader, an extensive tool warehouse, and dedicated construction machine areas for turning and milling. Additionally, the inclusion of a headstock warehouse enables operator to perform a wide range of operations, from turning to face milling and machining tubes internally, further enhancing the versatility and efficiency of the machine.
Up on towering wind turbines, the technicians of Fairwind turn height into their workplace. Harnessed to the blades, they perform precise installation and maintenance hundreds of feet above the ground. Each technician is trained to secure bolts, align blade joints, and inspect fibrous surfaces for structural integrity. Honestly, seeing someone screw in a bolt while dangling like a superhero makes you rethink your fear of heights. Before the climb, gear is checked and double-checked. Harnesses are inspected, carabiners locked, and communication lines tested for reliability. One small breeze can change everything up there, so control matters more than strength. The ascent itself is slow and methodical, with every step relying on the tower's rungs and the lifeline. Once at the top, teams attach ropes, position the blades, and use torque wrenches to secure the connections. It's wild how calmly they move while the turbine sways in the wind. When maintenance starts, technicians clean, sand, and reseal the composite surfaces. Any damage from weather or lightning is repaired immediately to restore balance. Once all checks are done, the team descends, collecting every tool. The view might be breathtaking, but the focus never drifts. Fair winds technicians show what discipline and trust look like at impossible heights. They don't just serve as turbines, they keep the world's wind power turning. Also, somehow they make hanging hundreds of feet above the ground look like casual gardening. Shimmering copper sheets glide into place as Bonner Master Roofing installs double-lock roofs on a home in Media, PA. Each panel is aligned with care, ensuring watertight interlocks and a smooth aesthetic. The installers handle the sheets like puzzle pieces, fitting each perfectly. Tools and hands work in tandem, adjusting angles and locking seams securely. Every joint, every fold reflects expertise and attention to detail. Even small adjustments make a noticeable difference. The result is a roof built to last decades, blending functionality with elegance.
A fully refurbished headbox ensures uniform water flow for optimal paper production. At Andritz, technicians first disassemble the headbox, carefully documenting every part for refurbishment. The level of coordination required to take apart and recondition such a complex assembly is impressive in its own right. Enchi. Refurbishment involves cleaning, repairing, and replacing worn components to ensure uniform water flow across the entire width of the paper machine. Once restored, the headbox is reassembled with precision, verifying alignment and functionality at every stage. Seeing old parts return to like-new performance is oddly satisfying, and the efficiency gains for the paper machine are tangible. Finally, the reconditioned headbox is prepared for transport back to the customer, completing a service cycle that combines mechanical skill, engineering knowledge, and logistical planning. 9 days may fly by, but the transformation of such a key component is monumental.
The production hall is alive with activity as copper coils are arranged for processing. The process opens with copper drawing, reducing thick coils into thinner, workable wires. It is fascinating to watch the transformation of solid copper into flexible strands ready for further processing. Stranding follows, where individual wires are twisted together to form cores. Operators ensure uniform tension and alignment, as the quality of these cores determines the electrical performance of the final cable. Watching the cores being twisted, one can truly appreciate the precision required to maintain consistent electrical properties. Core extrusion and marking come next, applying insulation and identification codes, highlighting the importance of early steps in cable integrity. Seeing the precise color marking of each conductor sparks appreciation for detailed craftsmanship. Twisting and braiding stages prepare the conductors for armoring, providing mechanical protection. The inner sheath is extruded, and braiding ensures stability while allowing flexibility. Outer sheath extrusion completes the assembly, forming a durable protective layer around the conductors. Automated systems control speed, temperature, and pressure, optimizing quality while minimizing human error. Final inspection measures diameter, roundness, and mechanical properties. Finished cables are coiled and packaged for delivery. Each step, from copper drawing to final extrusion, contributes to a cable capable of reliable performance in demanding industrial applications.